Welcome to this special seminar within the Structures Seminar, Graduate Student Seminar Series. We have the pleasure and the honor to have today here with us one of the Neil Armstrong Distinguished Visiting Fellows, University, the College of Engineering, has several, 6 I believe at this count, and they are appointed for a period of 3 years to interact and visit Purdue, interact with faculty, graduate students, and get involved in all sorts of academic related activities, such as writing papers, joint proposals, and so forth. And that's exactly what Dr. Randall W. Poston has been doing for the past 3 years. He was appointed officially in January 2019. He's been with us multiple times. So I encourage you to go to the website and search Neil Armstrong Distinguished Visiting Fellows, and you get all sorts of information about this very important program of the Dean's Office. Suffice to say, these individuals are very accomplished. I know I could spend here, and I told Randy I wasn't going to take 15 minutes of his seminar time to do this. In the introduction, but suffice to say, he has reached one of the highest levels in engineering. He's a member of the National Academy of Engineering. There are very few of those, and it's not that easy to get there. So today, we have him here to give us his seminar on a very interesting and relevant topic as we face the grand challenges in our world today of climate change, energy, and resilience of our infrastructure. And all of those get kind of touched by this kind of presentation. His topic is wind damage of solar power arrays and required repairs. With this, I have the pleasure to turn the floor over to Randy and introduce him. And please, join me.
Well, thank you, Julio. It's my pleasure to once again be on campus. It's been a year and a half. I was here right at the end of February in 2019. Seems like an eternity ago, but and of course we know what happened in mid-March of that year. I didn't have this on the. I didn't want the dean's office when they sent out the thing to give an explanation of my talk, but it actually is, and now for something completely different. And I say that because everybody generally thinks of me being a concrete person, but occasionally we have to do steel and do masonry and do timber, although our main work is in the kind of the structural concrete field and so forth, but got involved in this very interesting project, and as Professor Ramirez says, it is fairly timely given the green energy future that we're looking at for the country. And now for something completely different. Anybody know where that comes from? That's actually something that's a Monty Python movie. So back from 1971, that shows my age, and but I thought it was appropriate since I'm going to be talking about wind and steel today. So I'm going to talk a little bit about an investigation we did, and I'm not going to spend a lot of time on that. I'm going to concentrate on some issues of repair that we had to do to these arrays. That included doing a series of coupler tests, and I'll explain what these couplers are, and then summarize what we ended up having to do. Boy, that was unusual. How did that happen? Apologize. My system is having a conniption here. Okay, so these are 50 megawatt facilities located in the Phoenix area. One is Luke Air Force Base, and the other is Desert Star over in this area. And there was a wind event that occurred and had a lot of damage, and it only occurred at Desert Star. It was kind of a microburst in climate wind event, and then the Luke Air Force Base, though it's the same system, identical, but it did not experience any damage. So here's a bit of a picture. This is the one at Luke Air Force Base. You can see after the event, everything looks intact and looks in place. Here we have these solar arrays out at Desert Star, and you can see a lot of them have, the panels have come off the system, the support system, and you can see a fair bit of damage. And we'll talk a little bit about why the damage occurred where it did. There's some trends that we were able to assess from visually counting and looking at where the solar panels came off the. Have a short video, and if I can get this to play. Warranty and guarantee that this would be serviceable for so many days a year, and every day it's not putting power out to the grid was in essence, a liquidated damage like you would have in a new construction project. So they were going to have to pay the Arizona Power Systems for every day that it was out of use. So obviously became important. After the event, the thing shut down. And not only were we having to deal with the kind of the support system, but we had other people had to deal with the issues with the it's always kind of funny to say the electricity when they're generating electricity, but they had to get everything back online in order to be able to be functional. So this is Luke Air Force Base, the coupler, and again Desert Star. This coupler that joins this torque tube, so it's the same one at both facilities, exactly the same, essentially the same number of panels. I don't know why it's being obstinate. This is Desert Star. You can see when you look at it in broad scope here, out view, lots of panels, something like thousands of panels. That's all I can remember at this point. But there are lots of panels. There's each one of these represents a given array that we were looking at, torque tube, and so you can see there's it covers quite a bit of area in the desert. In terms of the design and how there's a little bit of a difference for the ones that are on the what we call the exterior exposures. These would be exterior exposures. In ASCE 7, when you look at wind, they have different ways to look at the wind pressures that develop. If it's an exterior exposed, you can imagine if a wind is coming this way, it can create turbulence off this one, but there's nothing outside here that would create that turbulence. So this has to generally be designed for higher pressures. The rest of these are generally designed for a little bit lower pressure. Here's a given array of field, and when we look at the you can see this would be kind of a shot of that area on the previous, again the exterior array, and then these interior arrays. And then focus in more. This is a given system orientation. Here's the exterior row on the upper location here, and here is the interior row there. And again, this is you can see the support system. Here's the drivetrain that moves these arrays on the torque tube tracker system. I have no idea why this. Did I bypass anything? Maybe not. So this is an image from a drone that was flown afterwards, and you can just kind of get the extent of the number of panels that were damaged. Most of these were released, and I'll talk a little bit about why that happened. Others were just distorted. These sit on purlins, in essence, that are attached to the torque tube, and so some detached. Those are the empty spaces that you see. Other ones were just distorted in their plane. Well, I'm going to go to the old-fashioned system here. I'm not sure why it's not working, but anyway, let's continue moving on. Couple shots. So here's again the solar panels. These are the purlins that attach to the torque tube. You can see the drivetrain and these coupler devices, and we'll talk at some length about those. And you can see some of the damage on the purlins. Typically we would see the ones that did not release, we might have some distortion, basically relative distortion between the edges of the panel. They should not be that way, so there's some deformation that's going on, not only in the purlins, but also in the solar panels themselves. They were racked at times. They're fairly flexible, but there was some deformation in those. So when we went out site, looking around, trying to figure out what the heck happened, we went to areas where we could, particularly at these couplers, we honed in on those very quickly. You can see some relative distortion between one side of the torque coupler to the other side of the coupler. And this coupler is, you can see here underneath there is you can see ever so slightly some distortion that's occurring. It's actually a U-shaped piece. There's an interior tube that you can see there that fits into the HSS tube. And this is a little bit closer shot of the distortion that was occurring. And of course you think, well, this was designed for 110 miles per hour, and the wind event, the best records we had from a nearby weather station said at best the wind was probably only in the range of about 45 miles per hour. So didn't seem to compute why would we have this much distress when it was, in theory, was designed for 110 miles per hour. So again, just kind of gives a visual, and we'll look at some statistics on a frequency diagram on where a lot of these panels in the various arrays were releasing or distorted. So a lot of, you could draw, these are the conditions for the support for the exterior rows. And you can see when we go in and start plotting out, we did it initially when we went out there, we had a pretty small sample for our first site visit. And then the contractor got a drone and did a survey, and we could start counting up. And what we found is that you could see in terms of the frequency, most of them tended to happen. There are 20 panels per solar panels per array. A lot of them were occurring right at this location number 12. You had a little bit of a hump over here at 3, and then of course at the ends there's really no distortion that's occurring. There's no coupler there. Then there really wasn't distress. So we see a lot of distress that's occurring at about the 12th panel from the end. So this is the original coupler. It's got it's a bolted connection. It's got an interior tube that goes into the outer tube, and then there's a U plate that you can hear is ghosted out that goes over that particular connection. So the thing is, though, that particular coupler, it's really only going to engage this inner torque tube after it moves, right? It has to go through a certain amount of distortion, rotation specifically, before it's going to engage in this tube. And if you look at just the U-plate itself, it has very, very low stiffness. I mean, very highly flexible. You have to get to 2 degrees or plus or minus if the bolts are centered in the oversized holes. And then once you engage it, then that stiffness, of course, goes up. That's all fine and good, but it's like, well, why was this designed that way? And then the secondly is, would you want to rely on kind of distortion and movement in order to have a device? So again, you can notice the distortion that was occurring, and so we could go to all the couplers out there, and we would typically have seen this distortion in that outer U plate. As that wanted to rotate and move, it deformed laterally, and we'll see what happens in actual application. The panels at the splice. We could go out and measure the slope. You can see this particular panel here. You can see some evidence of how it's kind of racked. It's got the frame itself is you can see here this looks higher here and lower over at this location. And even in the same panel, you would have different rotations or different angles that occurred. The stow position for these panels were originally, of course, we'll talk a little bit about the wind, but it was originally designed to be at 30 degrees, and then it was later changed to be only 15 degrees. So that would be, in a wind event, it would go to the stow position in order to weather, so to speak, the wind event if the winds got over a threshold value. The connection there's just these clips between the solar panels here, this little clip here, and honestly, in my mind, not a very good positive connection, because it's really relying on friction, and what you can see happen. This one's okay. You get equal sides. It's being held in place by the clip. But over here you can see the movement of this clip, and once this clip moves off the frame of the solar panel, that's it. It releases. And so once you release it on this side, you're probably going to release it on the other side, which releases it on the next side, and so forth. So it's kind of ends up being a kind of a propagating failure, if you will, in terms of holding down the panels. So not the best connection. You would think they would use screws or something that would be a positive attachment to the panels. So in wind, you probably know that the pressure that's being developed on the panels is based on essentially the square of the velocity of the wind speed. And again, so this was designed for 110, and yet the wind speed actually was, I said 45 earlier, was only a mean average of about 40 miles per hour that created all this damage. So way below, and you can see well below whatever pressure presumably it was designed for. So not there clearly was something wrong in the design. So the overall failure analysis and investigation, I said we were able to pinpoint that very quickly. You had twist across that coupler because it had to engage that inner tube, and it was from this wind-induced torsion. As you can imagine, if you got these stowed at even at 15 degrees, you're getting wind pressure on that, and the torque tube goes to a fixed location at the ends, and then is in essence flexibly like a hinge condition at the very end, so you have zero torque there. You unseated the clips, and once you unseated the clips, then you're able to have release of the overall panels, and you can see in the last one the overall loss of panels. It didn't propagate completely through the whole array, but it typically would go through a number of adjacent or contiguous panels as this happened. So that's kind of the investigation side, and again, I don't want to spend too much time on that. The more interesting part was, our client going, what are we going to do about this, and how are we going to fix this? And by the way, we're paying whatever they were paying, $10,000 a day to keep this plant facility open. So they were in a hurry to, as it turns out, the power company was real good, and based on their proactive nature going out and getting this fixed, they didn't worry about the liquidated damages for having the facility down. But we needed to replace the coupler. That coupler was definitely the issue. And I mean, you think about that. If you have a torque tube and it's a continuous member, but you put a splice right in the middle of it, you got to have a connection that can transmit and take that torque as if it were a solid torque tube. I mean, it's obvious. So we looked at a couple of different options. The manufacturer, interestingly, of the system had that original one. Since then, she obviously had an issue at other facilities because they came up with a retrofit option, which was interesting. As okay, you must have had some problems, so maybe something was wrong. And then we developed our own option, and then we did a number of load tests, and then I'll finish up again with the summary. So this was the manufacturer's replacement coupler. It's kind of a clamshell, two pieces bolted together, as you see here, across that connection. On paper it looks perfectly reasonable, but really would it have the capability of being able to transmit the torques that are going to go through this tube. This was our pivot coupler. We developed had bent plates that we ended up bolting through with the bolts like in the original connection. And then we also welded, you can see, at this location and this location. And we felt this was going to be the one that was closest to what a integral torque tube would be in terms of the overall torsional stiffness. Some stitch welding in between, you can see here in elevation, and then those bolts. So the load test. So our clients, we decided early on, and it was really with the client, or the contractor who built this, making the decision that they wanted whatever coupler was going to be most like whatever the stiffness of the torque tube was. That's what they wanted to replace it with. Said perfectly reasonable. So we went in, and so we thought about disassembling some units, sending them to a laboratory, getting them tested, or the other idea, and the contractor actually said, why don't we just build and do the load test out at the facility. So we quickly built, they gave them some specifications for a foundation, for some sections that we could bolt off of, disassembled some of the torque tubes, went out into the desert, and I guess it was probably July doing this work, so you can imagine how hot it was. working on that, but we ran a series of tests out on the field that included flexural test and torsion test. So it took 6 days to run 6 different tests. We had 3 different test configurations, which I'll describe. Again, we didn't have any issues with Luke Air Force Base, but the same problem, if they ever had a wind event similar, it was going to have the same issues. So it was clear the couplers just did not have the torsional stiffness they needed to, and they needed to be replaced. There were some almost 1,600 couplers between the 2 facilities that had to be worked on. So that is, welding is not necessarily the option you would think of, but it was the only way we could really come up with really mimicking really what that torque tube was needed at that coupled location. So we had these, again, different couplers. The original coupler we tested as a benchmark. We had the manufacturer replacement coupler and then our pivot coupler. And then we used the same protocol on sections of the torque tube had a flexure, a torsion, and a combination of flexure and torsion. So we went out, got, these are all interior, you remember exterior were the far ones on the leading edge of where a wind event could happen. We went to an interior section and disassembled 3 different arrays and took a portion out of it to include the support condition and the link for the coupler in order to do our test. So this was the overall load test protocol for the flexure testing, just a moment, and we put on a moment, let it sit there, move it, increase the moment, sit there, increase the moment, let it sit there. This is the overall configuration where you've got the support. This is without the torsional restraint, and then the support without the torsional restraint here. Here's the coupler, and we applied third point bending in these particular flexure tests. So we applied the vertical loads by hydraulic rams and monitored the movement through potentiometers, string pots, basically, in order to be able to develop load displacement curves and thus derive the flexural stiffness. The load test protocol for the torsion was similar, but we were doing it with torsion. We'd rack it one direction and back the other direction. The difference here, we have a support with the torsional restraint, and then at the other end, you apply torsion. We applied the torsion by a pair of hydraulic rams and included the coupler. And again, we monitored the loads or the torque being applied. And then we applied the torque through a series of 2 rams. So here's again the setup on the left-hand side. On the right-hand side is the applied torsion test, and you can see this little cantilever section off here with the ram on one end and the other end, and so you can imagine as we engage the hydraulics, it puts the torque into that tube. So we're monitoring the twist and monitoring the movement, or in this case the rotation, through a series of potentiometers. So, having some limitations, not being in a lab, we had to decide what was the end game or the end point of those tests. It could be a structural failure. Something happens and it explodes. Exhausted our brakes. We exhausted the stroke or the rams that we had, or there was, of course, any safety concerns. We would immediately stop test. So those were the 3 hard points that we had in terms of our protocol. So first, we went in and looked at the original coupler. So we did both. This is before the test, and then you can see after the test, you can see it really is acting like a two rigid bodies almost. I mean, there's very little bending in that section. It's essentially just the coupler is moving up, and you got two straight lines more or less. So not what you, even though there's not necessarily a lot of there is bending in these connections, but you know, the real critical point is going to be how is it going to behave in the torsion test. So if we look at the theoretical flexural stiffness compared to the load deflection curve, you can see we're for the original coupler, it's, you know, it's okay for a very low level of load, but then it drifts considerably off where where it should be theoretically from a stiffness perspective. Some of the shots of what you would see underneath here. You can see some of the deformation that's occurring at this bolted connection. You can see it almost dishing in. We had some slip around some of the washers. You can see the amount of space between this U-shaped piece and the torque tube itself. And again, on the top side, you can see that dishing that's occurring, distortion, deformation that's occurring around the bolts. In the torsion test, before the test, we set the purlins out level, so we have to each other, so we had a 0 point, and then after the test you can see some of the rotation that has occurred over from one side to the other at the purlin, so a fair bit of rotation. And when you look at that overall load or torsion deformation or rotation curve, this would be the theoretical calculation of the value of the stiffness of the torque tube, and you can see how this is actually behaving. So it became clear the original coupler, in their mind, we believe that the design engineer thought that coupler was as good as having the torque tube there, and it was clearly not the case. At a very, we're only getting 40 miles an hour, we're getting this gross distortion that's occurring. They simply blew it. I don't know how else to say it. They were just not thinking clearly. So it wasn't going to be able to sustain the torques that it needed to at 110 degrees, much less or 40 degrees, or 40 miles per hour, much less 110 miles per hour. So just to give you a little bit closer shot of that torsion test, we go in here, clip it out, and again you can see this would be the theoretical torsional stiffness, and this is how it's actually behaving. And we're rotating it through with the hydraulic rams one way and then back the other way. That's why there's what looks almost like a hysteresis loop in that connection. So again, some of the looks underneath there, you've got distortion between right here at this location. I mean, you think about this. This is like you have a tube here and you got a cut there. You do have the internal tube, but you think about torsional stiffness, the difference between a solid section and a U section. Calculate what the torsional stiffness of that. This is significantly lower than what you would have if it's a solid tube. Again, we can see some slips at the washers. You can see things happening at the coupler between each side of the torque tube, and some permanent distortion that's a relative rotation that's occurring on each side of the torque tube in the purlins. Again, distortion. You can see here movement of the washers and the bolts. You can see the distortion at that location. So this is in service. That's after testing. So we were comfortable that we nailed what was happening in the field, what happened during that wind event, and we're able to demonstrate that through the testing of the original coupler out at the site. So we just had a great that we can put a GoPro camera on everything and take a look at it, just start videotaping any and everything, and you can see what's happening in terms of the distortion. And when discussing this with the engineer of record that designed this, going, oh well, we designed this as a fuse. I'm going like, well, what do you mean a fuse? This is just, you couldn't even, it's distorting. You got these panels going off. That is not a serviceable structure. You're losing 25% of your panels at a 40 mile per hour wind speed. That's not a serviceable structure. It's got to be able to fit for its intended use, as we say. So if you look at, there was a little bit of, interestingly, a little bit of difference in when you have 18 kip inches of torque in each direction. There was a little bit difference of angle in terms of the rotation. In this case, only 2.5 degrees across the purlins, and this only 1.5 degrees. So just a little bit of asymmetry, if you will, between the two sides. So now when we, again, look at the relative rotation adjacent purlins across the coupler, again, you can see that we're getting a lot of rotation, very non-linear rotation as you increase the amount of load. So next we went to the manufacturer's coupler. After all, he was going to be offering those couplers for free, and he wasn't going to do the work to put them in. But we told our client, it may work. We're not convinced, and so we tested the replacement coupler as well. So again, we repeated the test, went through the flexural test, and again, when you look at the flexure test with this clamshell here, it behaves almost like it's just a stick, rigid body on each side. All the action is occurring at this coupler in a flexure test. It did perform a little bit better in terms of its overall stiffness. If this is the theoretical flexural stiffness, we're closer to that line, but we're still not there. So there was still some inherent lack of flexural stiffness in that connection. You can see our favorite whitewash, seeing what's happening at each side of the connection, seeing what's occurring out near the bolts as well. Second step, of course, doing the torsion test. This is before the test. Again, we align the purlins, and then after the test, at about 95 kip inches, we got to 5.5 degrees, and that was we stopped the test at that location. Again, looking at the overall behavior from this test, this would be the theoretical value if it was working as a solid torque tube. Again, we're not quite on there. Again, it did better than the original coupler, but still lacked some inherent stiffness. And of course, if you really wanted to know how this was going to behave at 110 mile an hour wind, you'd go run a wind tunnel test, right? Well, we didn't have the luxury of really doing that. So our thinking was, and what we conveyed to our client was, the best, we looked at their design calculation, and it was clear they assumed if you able to take that whole torque across that member as a solid tube, the stresses are fine. Okay, so in our mind, we said we got to mimic what needs to be done in a solid torque tube as if it had no coupler. So the torsion test, again, when we did a little bit of a snapshot, you can see it goes off, it's linear at first, and then we deviate from the theoretical straight line. Again, looking at some of the damage, some of the stresses, we're clearly getting some yielding at isolated locations, getting some separation between this plate. You can see whitewash coming off here. You see some of the distortion that's occurring. You can see movement of the washers in the around the bolts and the washers. So finally, we're getting back to looking at our the replacement coupler that Pivot designed. We ran the test. Again, in the Flexure test, in any type of connection, you can see a little bit more natural curvature in the beam with this connection than we saw on the other ones. Still not absolutely perfect, but as close as you're going to get. And then when we run the Flexure test for this, you can see we're getting pretty close to the line. Again, better than the other two, but still not absolutely perfect. Here's just some shots showing some of the damage. We get a little bit of, you can see some localized yielding here, locations. You can see a little bit of separation between this new bent steel plate that we added as our coupler and the torque tube. So a little bit of separation there. In the torsion test, you can see the relative rotation is much less as what we would expect between adjacent purlins. So before test they were level. After the test we had that smaller amount of relative rotation. And when we look at that particular this is the theoretical line that I've been plotting for the torsional stiffness, if you will, and you can see that we're getting pretty close to mimicking what we needed for that torque tube. And again, that's a close-up shot of the torsion rotation tube, and very good, very close comparison between the lines. So if we compare all those, I got accused by the engineer of record when we made a presentation that green, blue, and red were significant. Red, of course, the red one was their original coupler, blue was their next coupler, and green is our coupler. And he's going like, "Oh, you're biasing what you're presenting because you're showing it as stop and go, you know, kind of thing." I was like, "No, we really did not think about what colors we use for plotting these curves." So we had no concept about that. But I think you get an appreciation when you put them all together in the Flexure test. The original coupler, their replacement coupler, and then the pivot coupler, we're getting closer and closer to the theoretical stiffness. Same thing for the when you look at the torsion test, you can get a sense that, and that's really where all the action was occurring, was in torsion on this member. Very far off on the original one, a little bit better with their replacement, but very close with the retrofit option that we came up with. And again, if we zoom in on that compared to the theoretical torsional stiffness, you can see we have pretty good agreement in that particular case. The purlins, you know, you look at the overall rotation. You have to look at the rotation of the beam and the rotation of the coupler, and we had enough string pots and whatever that we could determine what was happening on each side of the coupler. So the load test summary, the original coupler was just not stiff enough. I mean, it just didn't perform, and especially as you could in torsion, which was really the main, you know, kind of the main action that was occurring. Sets forces being the vector forces or moments that were occurring on that tube. There was just a lot of distortion that was occurring locally and at the coupler, and you could see that we were able to compare what happened in the field with what we were able to observe in the load test. The pivot and the manufacturer replacement couplers were both stiffer, but the pivot one was not much stiffer, but stiffer than the replacement one. And what ultimately decided at the authority that owned the facility had their own independent engineer come out, and he witnessed the test, and he was very adamant that the only way that the power authority is going to accept it was if they used the pivot coupler, albeit it was going to be a fair bit more expensive. We did a replacement of those clips that were the you may remember that we came up with just one of the contractors folks who builds these things came up with this little idea of having this little push through down here to keep them separated, and it actually worked quite well. So in summary, we had one field that was extensively damaged. We had another field that was not damaged at all, but they had the same system, and they were designed for the same 110 miles per hour. So it's like, okay, what do you do? Well, the only thing the contractor could do is say, we're going to replace all the couplers. So that was, again, about 1,600 couplers that had to be replaced between these two facilities. The damage and the pattern of damage and the damage that we saw were very consistent with what we saw in the field from the wind event and what we were able to demonstrate through the testing. The couplers did not have enough torsional stiffness, which resulted in that significant relative rotation between the panels and particularly at the coupler. The couplers were replaced, and they were at least consistent, more or less consistent with the original torque tube properties. We did the load test to verify that what the replacement options would be, and again, the one from the manufacturer wasn't quite as stiff, and particularly in very close flexure, but much less further from the mimicking the actual torque tube properties with that particular retrofit coupler. The original coupler performance was not consistent with the existing torque tube, and we were able to replicate the damage that was observed in the field with what we observed in the actual test. So with that, I'd like to thank you for your attention, and be happy to answer any questions that you may have. Thank you.